Good afternoon, everyone. I'd like to welcome to the stage David, who's traveled all the way from Oregon in the States to talk to us today about speculative execution side channels.
Thank you
Over to
very
you.
much. Thank you. It's wonderful to be here at FOSDEM. I've heard about this conference for many years. This is my first time being here, though, so I'm a little bit excited and a little bit intimidated by all of you. But this is a great room so that all the introverts can sit as far apart from each other as possible. Awesome. It's my kind of room. Different from the security track yesterday where everyone was really packed in. I really want to acknowledge, by the way, before we start, this content was created by somebody in my group, Antonio Gomez Iglesias, who did a phenomenal job doing the research and putting the slides together. He would be here, but he was given a talk the same weekend in Washington, D.C. For a bunch of security hackers, so unfortunately he couldn't be here, but I'm delighted to make use of his great material. So anyway, I wanted to shout out to him. And in the spirit of FOSDEM, I'm going to be talking a lot about how collaborative effort goes into a lot of what we're talking about in this subject, and so it's very much a part of how we can cooperate together, and we're really interested in working with folks on this. Intel Corporation pays my paycheck, so it's important that I put this slide up. However, I want to say up front that I'm not a spokesperson for Intel in no way, shape, or form. This is the first time I've actually presented this material publicly, so please hold back on the trolling a little bit. I know one of my friends said she might be here just to troll me, but I don't see her, so maybe I'm good. So the other thing I wanted to say, because I'm not here speaking specifically as an Intel spokesperson or something like that, when I say we in the talk, and when I'm talking about we, it's not Intel. When I refer to we, it's the group that I work in. It's a group that works specifically on these areas of side channels, speculative execution side channels, other sort of very severe security issues or functional issues that we're trying to resolve. So when I talk about we, that's who I'm referring to. All right, well, let's start. When we talk about speculative execution side channel, we need to talk about, let's start with this barista. This barista is a very good coffee maker. He really wants to do a great job for his customers. He notices you come into the coffee shop at 6:29 a.m. every morning on the dot. Now, I don't know about you, but I'm not sure I'd be there at 6:29 every morning. But every morning, you're in there at the coffee shop and order kind of an unusual drink, a 4-shot, half-calf, cinnamon latte with almond milk or something like that, right? Kind of unusual, but 6:29 every day. And then, so he prepares the drink in advance, has it on the bar right at 6:29, and this goes swimmingly for a while, and then one day you go to work, maybe had too much beer the night before and don't make it at 6:29. By the way, I've heard that there's supposed to be beer at FOSDEM. I haven't seen any proof of that, so, anyway. So the drink goes to waste, so he simply pours the drink down the drain, throws the cup in the trash. But if someone's able to look in the trash and see the cup in there with the drink, someone might be able to intuit something about you based on the information on the cup, right? It was thrown away, but they might be able to intuit something then about the data because of the metadata. All right, so by that same sort of analogy, when we're talking about side channels, the whole idea of side channels at a broad level have been around for quite a long time. And they're really an attempt to try to collect information from some other unauthorized way in the computer. And that it really does target all levels of hardware and software. When we talk about the use of power, the amount of power that a computer uses varies on the instructions that are being run, right? If you're running more complex instructions, the computer tends to take more power. And it's been shown you can actually intuit what the computer is running based on the amount of power that's consumed. Now, sound, the sound of someone typing on a keyboard has been shown to actually be clues to help discover what passwords are. The caches are various microarchitectural features within the CPUs that allow someone to be able to perhaps just to determine what might be in memory. And then time is how long things take. If things take a short time or a long time, you can determine things about what's running on the computer. Now, I was thinking about this morning in terms of power. If you can figure out what's going on the computer based on how much power is consumed, maybe, would we try and mitigate that, I would think the answer would be no, because we want to try and save power as much as possible, right, for social responsibility reasons, if nothing else. We want to make sure that we limit the amount of power that computers use for the sake of using less power and issues of climate change and the like. But, you know, all of the, oh, I have to drink a bit of water. All of these side channels have similar characteristics. That is, that they require a set of deep system knowledge. There has to be an understanding about how the hardware software is implemented. It usually targets a particular implementation. So if you are typing on one kind of keyboard and you have the acoustics from that situation, you move to a different keyboard, you may be unlikely to determine the same amount of information. And typically for all of these, the system is working as it was designed to work. It's not like it's something that's an unusual kind of behavior. Someone has just been able to take advantage of some of these things. Now, when we talk about timing attacks, it's a particular class of side channels where you can say, well, if something takes a longer period of time versus a shorter period of time, can we determine something about what the computer is doing? Can we get a secret out of the computer based on that? This particular paper in 1996 by Coker was a pretty seminal work in this. He demonstrated that you could actually determine Diffie-Hellman, RSA, DSS, and other crypto keys based on timing. So that was in 1996, several years ago. Since then, this area of timing has become a very rich area of research. Even up to last year, people are using the amount of time that software takes to run to determine things about what the computer is running. So it's important to understand that, yeah, timing attacks are not a new issue, but there's a lot of research in a number of different areas because of this area of timing attacks. So what's new? January 3rd of 2018 was when we first got an indication of timing attacks that were taking advantage of speculative execution. What's new about these is that it's really a very innovative kind of approach to trying to create side channels in this area. It really addresses the hardware-software interface, and so that was an area of attack that was new, and again, targeting speculative execution. Now, as we think about this whole area, notice I'm talking about POCs or proofs of concept. These proofs of concept really are a subject of a research paper, typically. If a researcher finds that there may be something that could be used as a side channel, there's usually a piece of code, and it's usually a proof of concept as opposed to an actual exploit. In fact, in many cases, a lot of these things that have become popular, there's a logo created for them, a cute name, and then sometimes even a theme song. There was one that came out in December that had a theme song that they sang as part of the conference. It was kind of entertaining. And so but relative to the actual exploit, there are not necessarily practical exploits that come out of these things. But in every case, all these are local methods. What that means is they're typically not methods that can reach across the internet or any kind of networking. They don't usually involve privilege escalation. It's not like somebody with unprivileged user can get root access or something like that through these attacks. And then typically they're only read-only access. In other words, an attacker can't change data or write data, they can only read data. So these are things in common. Now, when we talk about speculative execution, I actually took a walk with my sister in 2018. It was on a 500-mile walk through Spain, and she's a non-technical person, and I was trying to describe this whole area to her, and a non-technical person, she thought the term speculative execution was so funny. And I said, well, what's funny about that? And I said, well, I suppose if you don't know what execution is, yeah, okay, so it's kind of funny, I guess. Anyway, she thought it was hilarious. So there are a variety of classes of parallelism that are involved in the hardware. So instruction level parallelism is one of the oldest levels dating back, I think, to the 60s, where, typically we talk about a 5-stage pipeline for the processor. You fetch and decode instructions in the front end, and in the back end, you're fetching operands, doing execution, and updating architectural state. So the fastest processing you can do is when all those pipeline stages are running simultaneously. So you're fetching instructions and decoding instructions while you're updating architectural state and all the rest of it. So you can actually get multiple instructions per clock. That's sort of the goal of ILP. Out of order execution, by contrast, is where there's some sort of execution that's going on that requires some sort of operand that's not available, perhaps in a register. So the processor takes advantage of this and tries to execute some other instructions that are, after the instructions that it's waiting for, understanding the architectural state doesn't get updated until the end when all the instructions retire. And then speculative execution is that class of parallelism where perhaps there's a branch that you've taken regularly or jump you've taken regularly, and so the processor will attempt to, again, will attempt to execute those instructions, but won't update the actual architectural state of the machine. But what's true of all of these things is there's a period of time in which the microarchitectural state will have been updated as sort of a side effect of the speculative execution. And so microarchitectural means typically this is very specific to a particular processor, right? And it's going to be different for every generation of the processor. That's what makes it microarchitectural. When it becomes something that is standard, that's when it becomes architectural. That's sort of the difference. So this microarchitectural state is something that someone might be able to take advantage of as a result of some other activity that's going on in parallel. So let's get specific on this and talk about last May of last year. There was an issue that was made public called microarchitecture data sampling. Got to get the name right. Microarchitecture data sampling, or MDS. So this is an issue where there are certain certain processors that have certain buffers within them. There's the store buffer, the fill buffer, and the load port. So the store buffer is just a piece of memory within the processor that's used as a staging area for stores out of registers into memory. The fill buffer is used as a staging area in reading data into registers, and then the load port is used for memory and I/O. And so what we're doing here is what this issue is about is sometimes as operations go on these processors, there may be some stale data that's left in these buffers before or after one of these operations. And so it might be possible for a malicious actor to redirect this data to some sort of disclosure gadget. So you can see here that there's some data sampling going on with these little microarchitectural instructions. Now, in addition to this, there was another issue that was made public after May, what was called TAA, or TSX asynchronous abort. So this is a case where there's a technology called TSX. It's about multi-threaded applications. There's a technology in the CPU that allows you, if you have software that has multi-threaded software, often you need some sort of locking, right? You'll need a locking primitive, so if you have a critical section, you lock it so that nobody can change the data during that critical section. So this technology was created in order to speed up software that typically doesn't have contended locks, right? So this is a technology that was made available. Some software makes use of it. This was a case where an attacker could make use of this technology, where the attacker could use TSX and actually could figure out how to exploit, again, the same MDS issue, right? So typically, again, it's not used by all software, but it's something that's sort of available that was taken advantage of. Again, these are issues that are very specific to certain processors. But let me show you how the threat model works on this one. So my intention, by the way, is not to help you create an exploit, but help you understand a little bit how it works. So let's take a cloud scenario, right? So we're running in maybe infrastructure as a service, something of that sort. You have some code that's trying to leak information out, and it's running on the system. This is a 4-core server in the cloud. Each core has 2 hyperthreads. So what it's doing is running on one of the cores. So the victim has to actually be on the other thread of the same core. Okay. Now, in a cloud scenario, of course, typically those people running in the cloud don't have an idea exactly where their thread is running versus any other thread in the system. That's the whole idea behind cloud computing, right? In addition, they may not even know what the architecture of the underlying processor is. Most cloud service providers try to, don't necessarily like to reveal that information. So if they schedule you on a processor that's 7 years old versus one that was bought yesterday, then they can, charge the same amount of money for it. I think that's a great business model. But it doesn't mean that you can ever know exactly which processor you happen to be sitting on in a cloud. Then what has to happen is that by the way, the attacker has no control over the victim. The attacker can't actually control what the victim is doing. The victim is just doing what it's doing as part of its program. And that victim has to bring data in repeatedly. It has to happen, more than just one access. It has to have repeated access. Then what's required is that there's an actual small window of time to extract data. So it's not something that can happen instantaneously. It really has to take place over a period of time. But there's an actual small window to extract the data because, again, these are buffers that are being constantly overwritten as loads and stores happen. And then these two threads, by the way, have to share the same core for a period of time, extended period of time, so that the data sampling can take place. And then finally, after all of these requirements, the attacker has to post-process the data to see if it's seen enough accesses of something and says, maybe that's interesting, right? Because again, this is a data sampling attack. This is not like the attacker can control where the data is. It's just what happens to show up in these buffers. So after all of this, it might seem kind of a weak attack for somebody to kind of worry too much about this in a cloud scenario. And in fact, I think in a lot of circumstances, it is difficult to exploit, and why I think we've never actually seen any of these issues show up in the wild, so to speak, as an exploit. Now, I told you I worked in a group that works on this sort of software area, particularly open source, but also working with a variety of open source communities. So we actually, I did a panel discussion in Lyon at the, what do they call it, Open Source Summit Europe, I think is what they're calling it. And one of the things I did was I brought onto the panel various of the organizations and communities we work with. So we actually work with both the, communities like the Linux community, OpenBSD, FreeBSD, et cetera. We're also collaborating with a lot of the non-open source proprietary software folks that are doing system software and VMMs and things like that. So basically, one of the ways to address this issue is through microcode. So since the 90s, folks have been designing the CPU so they don't literally actually execute x86 instructions. The circuit doesn't execute, an add instruction or what have you. Instead, what it does is it translates that x86 instruction into a sequence of micro operations. And it's the microcode, it's actually in some sort of, space that's as the CPU is manufactured. But there's also an ability to update that microcode. So in fact, it's possible to update the way the CPU actually executes these instructions by changing the microcode. And this is a powerful capability because what it allows us to do is, in the field, allow us to update the very way that the processor is interacting with a lot of these areas. Now, in addition to by the way, along those same lines, that if you have a CPU, the microcode is different from firmware, from BIOS, anything like that. So what you want to try and do is keep your BIOS refreshed. Also, Linux and various other operating systems have the ability to update microcode live. So it's really a good idea to keep your microcode up to date. But one of the ways we're able to address this problem is through this area of microcode. And we have a large instruction set architecture, or ISA, and it's got some legacy instructions in it. So one of the things, one of the ways to address this was to take a legacy instruction, VERW, and that instruction, if you're curious, what it does is it tests to see whether a memory segment is writable. So the microcode actually enhances the VERW instruction to flush these buffers, the load buffer, the store buffer, fill buffer, and load buffer, et cetera. So what the VERW instruction now does with the new microcode will be to flush those buffers. We also, by the way, define some software sequences if you, for whatever reason, can't update the microcode, and all the software sequence does is do a bunch of loads and stores, and that effectively clears those buffers as well. So then, what's necessary? You need to be able to somehow, one other thing in the microcode was an addition of a model-specific register, or MSR. And these MSRs are there to give you data about the specific processor you're running on. And in this case, we gave the capability, there's a vector called I32 ARC capabilities, and it's a vector that sets bits based on is this issue present or not in the CPU, and do you have the capability of addressing it, right? So with the VERW enhanced capability and this vector of bits, you're able to put together an OS that can deal with this issue. So what we then did was, in working with the Linux community, collaborating with them and various other folks, we're actually able to use this VERW instruction every time you do a return from client to, every time you do a return from kernel to user space. So that kernel to user transition plus context switches, what this allows us to do is to say, well, every time user code, and basically this happens anytime you do a system call, you call into kernel, every return from kernel will then call this VERW instruction if the CPU is affected by this issue and will flush the buffer. So there's no possibility that some user level attacker can somehow observe data that's going on in the kernel. Ring transitions, yeah, that's what that basically is. By the way, the other thing we engineered was the ability to disable the mitigations, right? Because there are some conditions where you might say, well, I don't really need to have this, VERW calling thing. I don't really need to, slow down the ring transition, so I can just disable it. If I've analyzed the situation, in fact, I think this is really a good idea, is to say, what's the situation I'm running in, and do I even need to really run these mitigations or not? And so we engineered in the ability to, have a boot time parameters that let you turn these things off in Linux. Finally, the other thing we engineered in was this interface, basically user level, to again detect whether the CPU is vulnerable or not, and then whether the mitigations are turned on or off. To make it simple, there's an open source project called Speed 47. It's Speed 47. If you look in GitHub, you can find the project. It's called Spectre Meltdown Checker, and so Spectre Meltdown Checker.sh, and it's a script that we've been collaborating with to enhance it to, with all new issues as they come up, so you can call that and see whether your system is vulnerable or not. So after all of that, we can also engineer in the things with TAA. This is similarly, again, I talked about TSX being a technology. We actually worked with the guys working on the microcode to say if you want to even disable TSX, some systems will actually disable TSX by default, but there's also a control there that allows you to turn it on and off as well. And if you want to have TSX turned on, you can also use this VERW mitigation to basically handle it that way as well. So as I said, the work is collaborative. We work very hard with the Linux community and various folks so that before the issue becomes public, before this issue became public in May, we worked very hard on the patches to make sure that on the day it became public, Linux could pull in the patches basically into Linux. We had backports ready for the LTS versions of Linux. And the other operating systems that are, whether they're open source operating systems or hypervisors, bare metal hypervisors, or proprietary, everybody had something ready on the day the thing became public. All the software was ready to fix this, and the microcode updated. So that gives you a little insight as to what we're, kind of engineering with some of these things. Now, one of the things I think, I don't think our work is over when this happens. There's additional work that we're trying to do to try and optimize these mitigations. So, for example, if you look at that threat model that I talked about in terms of things running on different threads. Well, what if you wanted to actually try to fix that issue? Is there something you could do with the, for example, defining trust domains within the CPU? So a trust domain in this case would be, maybe I define it, a trust domain as each of my cloud clients, if I got different tenants running at the same time in a system, make each tenant its own trust domain. So each tenant would trust itself, but not necessarily any other tenant. Or maybe I would define some other model for using these trust domains. So one of the things we're working on in the Linux world is what we refer to as a core scheduler. And in fact, we're doing this development in the open source. You can go to LKML and read about this. We're partnering with DigitalOcean, they're a cloud service provider, and various others that are working on with us on this idea. And what the basic idea about this is if you have different processes, they'll typically by the Linux scheduler, they'll get scheduled on threads without really caring what the topology of the system is. It will just look at logical processors and schedule processes on those processors. But the idea of the core scheduler is if you can define trust domains, you can actually, it will say, well, if I've got two different trust domains, I'll make sure that two processes from different trust domains don't ever run on the same core, right? And one of the things that we're doing in this as part of our collaboration with the Linux community on this is that we're trying to do a lot of performance analysis as well and say, if you're doing this, you're using this core scheduler, what we found, the data that we found is that there's barely any ripple in the overall performance of the system based on a bunch of the workloads that we're running. But that's under both low contingent situations. What about in high contingent situations? Well, you may have a situation in a high contingent situation, and we're running extremely high systems here, where highly loaded systems. Here's a P6 that you can kind of see. Under the regular Linux scheduler, you might have it so that really anything can be scheduled anywhere. But under a core scheduler, under high contention, you kind of see, well, we weren't able to schedule P6 because we didn't find a processor that was, that didn't have somebody from another trust domain running on that core. So, yeah, in some cases for high contention, you may have some, idle threads, and so it's possible you might actually take longer under those situations to run. So we're doing a lot of, we're publishing all this information, by the way, on LKML, so I suggest go to the Linux kernel mailing list, look at the performance information that's been posted. One of the engineers in the group named Agata Gruza is posting this data, and interact with it, comment on it. We're trying to continue to post the information. I think this patch has a lot of promise, and I think it's going to be really helpful for folks, particularly in the cloud space or other spaces that really care about fixing this issue. But by the way, it's interesting that the other factor about the core scheduler is that it can be used actually for quality of service. This is something that I think is an interesting side effect of the fact that we're adding this capability to segregate processors based on certain characteristics, right? It may not necessarily be trust domains. One of the features in Skylake is this feature called AVX512. This is the ability to have large registers that are 512-bit registers, right? And large vector operations that go on those vectors. Well, because the operations tend to take up a lot of the chip, typically the amount of power that could be utilized tends to be higher. So the CPU tries to limit the total amount of frequency that's used on those cores that are running these instructions. So you can kind of see under normal scheduling, you could actually slow down, because if some of this AVX512 is running at the same time as a process that doesn't use those instructions, it brings down the top turbo rate. So we have something called turbo that's used for frequency adjustment. It will bring down the top turbo rate if it sees something with AVX512 running on it, right? So in fact, by using the core scheduler, what you're able to do is, if you can determine that the process uses AVX512, you can segregate it to its own cores, and actually the runtime runs faster in this circumstance, because the things that don't use AVX512 can turbo higher, can actually complete sooner. There's another thread over here, by the way, it says BW, that's intended to be a high bandwidth consuming process. Again, same kind of thing. It may not necessarily be AVX512, maybe it's using high bandwidth. So it can use this mechanism to control some of those things. And the interface basically it uses C groups, and this is the way, C groups, if you're not familiar, it's a Linux capability that's underlying containers. Someone who was going to be trolling me here said if she heard anything about containers, she was going to scream. She must not be here, because I don't hear any screaming. Anyway, it's one of the base technologies under containers, and by defining the C groups, the core scheduler will actually separate these threads onto different cores. So that's the way that works. So that's one optimization that we're working on. Another one is, I was going to talk about the rendezvous case, but in this case, I'm I'm going to skip this, I think, and talk about this idea of selective VirW based on the time I've got. So I said about this VirW instruction, just to remind you, the new microcode, what it does is every time you call that instruction, it clears the buffers, right? But in fact, doing it every time you go from a ring transition, in other words, going from kernel to user space, maybe you don't need that, right? If you're talking about different trust domains, like we did with the core scheduler, maybe it's unnecessary to clear the buffers every time you're running in the same trust domain. So we're actually working on something that's an enhancement to this VirW capability. So instead of, in this case, VirW gets called on every, context switch. Instead, if you're within the same trust domain, eliminate the VirW call. And we think this is an optimization that will really help accelerate systems that choose to, to do this MDS mitigation, right? This is a patch. I think we have not posted this yet, but we're doing some performance investigation on it. It's linked to the ideas in the core scheduler. And I think one of the things we're trying to develop is a good trust model around it so we can, publicly vet exactly what we think is going on here and what this is going to address. Okay. All right. Okay. The last part of the talk, I really wanted to refer to what you can do as a programmer to actually do something about speculative execution side channels and side channels in general. There's a lot of common best practices. By the way, I'm not a security, I'm not one of those people who've been spending, 20 or 30 years in security. I'm not one of those people come in and scare you right away about security because it's something I've kind of grown into over a period of time. I've actually been involved in open source majority of my career, which is kind of unusual for somebody my age to be able to make that claim. But anyway, I'll say open source of one sort or another. But there are some well understood practices. I keep hearing about various of these as these issues come out. And I think it's really important as you're writing software to take very conscious thought about these things. Probably the first and obvious ones is use well-maintained libraries. I've heard a lot at FOSDEM this year about OpenSSL, and OpenSSL is a great library. When Heartbleed came out, the community was very quick about fixing that particular issue in OpenSSL. But if somebody had an SSL implementation that was not as well maintained, they might be subject to various other issues relative to SSL. So identifying library, and then most programmers want to use libraries, right? We don't want to have to reinvent the wheel every time. Using well-maintained libraries is a key to making sure that issues as they come up get addressed, right? I say automate. Actually, it's Antonio's slide. He says automate, but I really agree. In this case, what we're talking about is if you have something that is fixed, is an issue you're aware of, you want to automate the tests that are going into making sure they remain fixed, right? One of the worst nightmares I think you could have in an open source environment in particular is you fix some sort of security issue and some other contributor accidentally unfixes it, right? And so being able to automatically test these things against your upstream and against whatever development is going on, extremely important. In fact, you could probably break something as well inadvertently, right? Only providing necessary information. If I log into a site and it's with a username password combination and it says invalid username, it's suddenly given an attacker, oh, that's interesting additional information. If it says invalid password, oh, the username is correct. I'll just keep working on the password, right? So actually, you don't need to provide so much information. So only providing necessary information so an attacker doesn't have the ability to, attack you further. And then including an update mechanism. This is incredibly important. I worked a number of years in the IoT space. This is something I find incredible as a lot of IoT products go out without ever being updated. And so malicious, and by the way, every piece of software, yours included, mine, every piece of software, the day it gets shipped has security issues in it. I nearly guarantee it. It's just been waiting to be found. And so this zero-day issues, what people typically refer to that, means that it stands to reason that there will be an attack in the future. So having an update mechanism. Now, that's a great engineering statement. In fact, you need the policy to actually do the updates and actually invest in the validation to make sure that your updated software doesn't corrupt something else, right, or brick the system or fixes the issue. So having an update mechanism is incredibly important. So then ensuring data can't be easily guessed. There's a variety of these. I'm going to actually focus on each of these in the next couple of slides. So the first of these is constant timing. Often we're found that, well, what's wrong with this piece of code in terms of this is doing a string compare and doing something with the result? Any problem with this? The more characters match, the longer it takes. Exactly right. So thank you. I wish I had a candy bar or something to throw to you, but I'm off of sugar right now. I'll throw a virtual candy bar. It's all the fault of the New York Times. So yeah, exactly right. The strcomp library function is optimized so that when the strings don't match, it returns immediately, right? So this is a case where you can intuit whether things about how much of the password matches based on how long the operation takes. So every time we hear about these issues, we hear use constant time programming to avoid side channels. Now it's a bit of a challenge because if you write your own function, so maybe you don't trust strcomp and strinComp to be constant time. If you write your own function, though, be careful of your compiler. Here's an example of some code that it's supposed to do constant time programming, right? What it does is it accumulates in M the XOR of every character, right? So at some point it will be set to 1, but the code is scanning through the entire string so that it takes the same amount of time whether the strings match or not. Okay? So this looks, pretty good. And the unfortunate thing is that compiler optimizations, what they'll do is they'll say, oh, once M is 1, it will never be 0. Right? So a lot of times compiler optimizations will drop you out of the routine immediately, but as soon as M turns to 1. By the way, how can you figure out whether this is happening or not? I suggest it might be good to become the friend of your friendly neighborhood disassembler. I mean, disassembling a little routine and see what the assembler has actually done. Assembly language is not too scary. No, but it's a good way to see how this works. By the way, there's one fix that will work for some compilers, was declaring, in this case, M to be volatile. And that's usually a clue to the compiler that, oh, something else, I'm counting on some other external behavior from M, so don't optimize away all these loops. Okay? So that's one technique. Volatile isn't always available in every C compiler. But what about Python? I like Python. If you're any Python programmers here? Oh, a few. Oh, good. So if you're looking at Python, this is a similar kind of function that's designed to be constant time string comparison in Python. The only problem is, again, depending on of course we all know that Python as a language has various different implementations. CPython is just the default ones. There are plenty of others, IronPython, PyPy, a variety of them, right? In general, though, this is, again, not constant time. So what can you do about that? It turns out since Python 3.3, there is a constant time comparator that's on the screen here. And if you needed an excuse to update to Python 3, well, I just gave you a great one, right? So just, update if you haven't already. Anyone still on Python 2? Oh, nobody. Awesome. Okay, good. So, okay. So, what else can you do relative to this whole deal of trying to, take care of side channels? One of the things you could do is if you have a secret, a good thing to do is actually eliminate the secret from memory. Right? Now, what's a secret? I had this question posed to me. Actually, I posted myself a little while ago. It was like, well, it could be a password, but it could be, my birth date or my income. It could be your annual income or your spouse's annual income or your girlfriend's annual income or whatever, right? So the idea behind this is to say, let's clear these out of memory. Now, one of the things that you can use is the memset library routine to zero out the memory. Again, at dash capo 0, no optimization. The compiler will call memset. But even at just the first level of optimization, dash capo 1, the call to memset disappears. And why that is, again, it's operating on something that the compiler says, well, this thing isn't going to be used, it's a local variable, so I'll just eliminate the call. So, there's a few other options, memset_s, can't be optimized out, it's part of the C11 standard. Not every compiler has it, unfortunately. There's also an explicit _B0 that can't be optimized out. Again, some of these options are useful to know about and test whether these functions are available in the compiler in your source code, and I think that's a good procedure. One other technique I think is very helpful is to clear the cache. If you have a secret, again, whatever the secret is dependent on the software you're writing, but clearing the secret out of the cache may be a useful thing. How do you do that? x86 has a couple of useful instructions. One of them is clflush and the other one is clflush opt. And most compilers have a way to call these instructions directly. And so this is a way to, again, get the system to work for you to clear some of those secrets out. Okay. Right. I think. Okay. So if you remember anything from today's talk, I want you to think about this. I want you to think about, does your system need to use these mitigations? Do you need to even have the mitigations turned on in your system at all? What's the kind of load running in your system? If you know all the software that's already running on it and you can't have a malicious actor running on the system, I think it's a good candidate for turning those mitigations off. I think the other thing to think about is if you're involved in Linux and open source operating system development, join with us to collaborate. We're very open for ideas. I love to get some additional collaboration on some of these things to help the entire community on these things. And if you're a programmer, I highly recommend you look at some of these techniques and implement these techniques to make your code less sensitive to side channels. So, thank you very much. Oh my God, times of questions. Shouldn't have done that.
Are you happy to take questions?
Sure.
We've got just over 5 minutes.
Thank you. Very good talk. You talked about the MDS mitigation where you flush the data when going to userland.
Right.
Is that the exact part where this performance loss comes from, or is there more going on?
No, it's really about so I think if there's any performance difference, it'd be that VERW instruction now clears these buffers, right? And so that takes additional time for the circuit to clear the buffers. And so if there's additional time, that's where it comes from. Yeah. And so that's why, as we're talking about optimizing, having, I should repeat the question. That's a good prompt. The question was for MDS. Yes, it's this enhanced VERW instruction that takes additional time. Yeah. Thanks for the reminder. Yes.
Yeah, so lately there's been a lot of sentiment in the security community that hyperthreading was a very bad idea. Do you agree?
Hyperthreading, again, from the standpoint of MDS, the question is, oh golly, can I think about there have been people who say, hyperthreading I don't want to quote what they're saying because I don't agree with them. So they've been suggesting hyperthreading is somehow dangerous. But one of the things I went through is with this threat model is help explain exactly what the issue is with hyperthreading. All of the steps that I went through on that. And even, if you decide, well, gee, I just can't tolerate, issues that come up with hyperthreading. I just don't want to take the chance. Then we're doing work with the core scheduler that's going to help, eliminate even those. So all the performance studies we've done is that, the core scheduler is actually much better than turning off hyperthreading from a performance standpoint and adds all the protection that's really needed for this issue. So that's a lot of the focus of what we're doing is making sure that there are no issues with hyperthreading. I don't know, is anyone turning off hyperthreading now? A couple, okay. I know one particular engineer, he's sitting in the back. I wanted to make sure that particular engineer knows that he doesn't need to turn off hyperthreading anymore in his product. Thank you for asking the question. It was awesome.
So another side channel is memory access, and it also has other attacks like rowhammer. And it could actually be interesting to extend trust domains into memory, so limit a trust domain to a memory channel or a DIMM. Do you have any plans to build such a thing?
It's the first I'd ever heard of it. It's an interesting idea. I think I'll definitely be jotting that down. I think it's a really interesting idea. Yeah. Yes.
Could you illustrate the current progress on mitigations against the recent cash-out attacks that partially circumvent the mitigations you presented against MDS?
So the question is the recent issue about that people were calling cash out. I have to think through my jet-lagged brain about exactly what that maps to. Yeah, what basically that, again, this is one of these great names. I got to think about the actual technology because the name sometimes is confusing to me. So in this case, this is another, as I understand it, this is another, I may not understand this correctly, so take this with a grain of salt. I think this is another MDS-like attack, so you can use the same kind of, strategy for it. But actually, this is another example where the microcode itself will actually fix the whole problem, and so there's a microcode update that will actually fix these entirely. Yeah. So it's a different area. It doesn't affect the other mitigations I talked about. Yeah.
Yeah, so a follow-up question to core scheduling. What kind of cleanup does it do when it hands over from the core from one security domain to another one? So for example, from one guest VM to another, if it's about
yeah. I got to be a little bit careful here because I know Jesse's looking at me and he's like, yeah, what's your answer on this one? Unfortunately, I don't know the answer exactly. There's the little I know about it, a little knowledge is sometimes a dangerous thing, is that the Linux scheduler has a placement algorithm and a load balancing algorithm. So what's necessary is that you have to both modify placement to make sure you're not placing things incorrectly, and also when you're doing load balancing, you don't load balance incorrectly. So both of them need to be modified, I believe, is the answer.
Hi, thanks for the presentation.
Thank you.
I have a question about the trust domains you mentioned, so implemented in C group, apparently.
Yeah.
That's the idea.
Yes. Mm-hmm.
Is the idea more to, like you had names like AVX and blah, blah, blah for C
512.
groups?
Yeah, the AVX 512 is an example. Sorry, I'm not repeating the question. I apologize. Go ahead, ask your question.
Yeah, the question was, is the idea for now to specify C groups, I mean, on the CPU part of C groups, only the subset of the instructions you wish to use? Or is the idea to be more generic, like, okay, this process I consider not trustworthy. I'm being a bit
okay.
imprecise on purpose here.
I think what I heard, and I'm having trouble hearing from back here, I think what I heard you ask is what's the sort of policy you might use for C groups?
Yes, because it seems to delegate the choice of who applies the policy to the users.
Correct.
I mean, sorry, to the program owners, let's say.
Yeah, correct. And what we're trying to do with this is define mechanism as opposed to policy. And so this is kind of a common design principle for Unix and Linux is to define mechanism and allow whoever is using it to define the policy. I would imagine a common thing to do in the case of a cloud service provider, for example, would be to have every tenant, if you're in a multi-tenant infrastructure as a service sort of implementation, is to have every tenant be in its own C group. And that way, that's probably not a bad strategy anyway. Yeah.
Okay, makes sense. Thanks.
Hello, thank you for the talk. I was just wondering personally, what are you doing to protect future generations of CPU by design against current attacks, currently known attacks?
That's a great question. The question is, what are we doing, not we in this case, what is Intel doing? Because we is, I'm just a bunch of software guys. So in the case of what is Intel doing to, kind of address these things with future processors? As we, as security researchers work with Intel, there's a major effort to look at the architecture overall and to understand, is this something that we can fix in future processors? And so, and it's not just, can we use the fixes that we've done at one point in time? We're constantly looking at ways of optimizing the mitigations as well. So that's a strong, area of work to make sure that future processors don't have any of these issues. Yeah, but of course, it's a constant area of work. I think I'm out of time,
I'll
yeah?
make that time. Thank you for fielding so many questions and for coming to talk to us today.
Thank you very much.